I will start in a few minutes. Okay.
Can I ask doubt on previous sessions?
Yeah, sure. If you have any, you can ask me.
Yes.
If you have any doubts, you can ask me right away. It's fine.
Yes. So in week 4,
Yeah.
question number 7, which of the following factors affect the emission and absorption rate of infrared radiation?
Emission and absorption. Okay.
Yes, emission and absorption. What? Because surface area, temperature, color was directly related.
Hmm.
He explained that.
Yeah.
But I felt that material composition also is uh, is relevant. Uh, I wanted to know how material composition is not relevant to this. I mean, it's
Okay.
made up of some basic material, right? It may also have that effect, the
Hmm.
emission or absorption thing. How it is not included in that, sir?
No, the thing is, emission means you're emitting, right? So
Mm,
basically, what happens is the amount of area which is exposed, that area is always in action whenever it's trying to emit anything. Okay. So
mm.
that's why color will be the factor, and the surface area exposed will be a factor, definitely. You know that, right?
Yes, yes.
Yeah. So now the inherent property of the material itself will decide what will be your emissivity, but how much it is emitting, that will be like decided by the amount of area exposed. So your material composition might affect in that way.
So it is directly related to the quantity.
You're saying quantity or the
No, I am asking whether it is related to quantity. How I wanted to know how the material composition again made up of some material which has that emission characteristic or absorption nature that is going to affect the infrared radiation, right?
hmm, yeah,
Affect or not?
yeah,
You are telling the
but
quantity of.
not directly. It won't affect directly.
Oh,
It will have an indirect effect. It's like that. Yeah.
okay. So there will
Yes.
be some material which will not participate in that.
Yeah.
So
Exactly.
that's why. Okay. Okay.
Hmm.
Okay. Okay.
Yes.
Thank you.
Yeah. This is from polymer reaction engineering only, right?
Yes. 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 Yes.
Yeah.
Yes,
No,
sir.
because
I log in a different ID. With the ID I used to log in, register is different, Hotmail ID.
okay, okay.
But this I'm using different ID. That's why I was waiting whether, I mean, if there is any difference so that you will not accept me or not.
Oh no, no, it's fine. Anybody can come.
Okay.
Anybody.
Okay. Okay.
Like I'm happy to admit anybody. It's just that you, if you are willing, then it's fine.
You can join. Yes. Yes.
Yeah.
I saw your recordings. I could not
Hmm.
make it all these days.
Oh, okay.
And I saw your recordings. It is very useful for me to solve that problems. Even after doing, I can able to answer. And this
Yeah.
question, after some research and all, I was feeling that material composition also included because I have selected. It's wrong for me, so I wanted to make sure that's it.
Oh, okay, okay. Are
That
you
time I
like
didn't attend the recording previously. I attended and got the mark. Then only I could see your recording.
okay? It's fine. It's fine. So, are you working on anything right now? Like,
So I'm a faculty in Anna University,
oh, okay.
printing and packaging technology.
Oh, you are faculty from Anna University,
Yes, yes.
like main
So
campus.
yes, CG. Yes.
Oh, you're from CG. I'm from AC Tech. I finished my bachelor's and master's from chemical
Very good.
engineering at AC Tech.
Very good. Very good. But you are doing PhD in Kharagpur, right?
Yes, yes.
Good.
I'm doing PhD in cars.
Sir is very fast. Getting information is, I mean, little difficult for me. I have to repeatedly watch this, this thing. But yours is very understandable, very
Okay.
nicely. Mhm.
Yeah.
Very good.
Thank you. Okay, then.
If you're able to come here, you can visit the department.
Yeah, sure, sure, sure. I'll
We
be
can tell that.
visiting.
Yes.
Like I'll be there maybe next month, I guess. So that time I can
Yes,
visit.
yes. Myself and Kanchana ma'am both registered for this course.
Oh, okay.
We wanted to use this course for our teaching because we are teaching polymers and related.
Oh,
Not
okay.
in
That's nice.
this much depth, but basically, yes, it will be
Okay.
very helpful
Okay.
for us. Thank you.
Yeah, sure. Okay, so today we will be taking a look at the fifth session, and today it will be based on mass transfer mostly. So it's like an intro to mass transfer mechanisms and basics of mass transfer. Okay, so I'll start.
I think yes,
Yeah,
maybe they
I,
join.
yeah. I hope my screen is visible to you.
Yes, yes,
Yeah.
yes, yes.
Okay, so we will be
Yes, you
only
are audible.
discussing. Yeah, so we will be discussing a few questions from the assignments, and maybe this will be helpful for you in solving any of the other problems also. So starting from the first one, which of the following parameters can be considered as a driving force for mass transfer? So basically, mass transfer is nothing, it's just as the name suggests itself, transfer of mass from one location to the other. So when mass is transferring from one side to the other, it's basically traveling in space and time. So basically, the space dimension can be represented by dx. And with respect to that, if you were to understand it from the Fick's law of mass transfer, then you can understand that the concentration difference uh, and the amount of mass moved from one place to the other is how you describe mass transfer. So we have four options here: concentration gradient, pressure gradient, temperature, and chemical potential. So if we look at all four options one by one, first we have the concentration gradient. So this is like the basics for how the mass is transferred in any situation, anyway. So if you have a waterfall, if you were to see, so waterfall is always going from the concentration where the place where it is having the highest concentration or any kind of gradient when it is being created. So from there, the water flows to the lower parts. So basically, we can understand that in a similar way for concentration gradient, and which can be said in terms of diffusion also. Next, we have the pressure gradient. So again, always the cylinder with the higher pressure, when you open it, all the pressure escapes outside. That is because there is a pressure gradient inside the cylinder and outside. So basically, the pressure gradient transfers all the mass from inside to the outside. So that is another thing. Next, we have the temperature gradient. Now, temperature gradient, uh, because of temperature gradient, what happens is you can have different effects such as conductivity, conduction, heat conduction can occur, or convection or radiation. So these are the phenomena which can happen because of temperature gradient. Now, a temperature gradient might not be exactly the direct source or the driving force of mass transfer, but it can indirectly affect in maybe creating some kind of mass transfer forces. For example, when you have the temperature gradient acting inside a fluid, what it will do is it will start heating, it will heating it, and because of the temperature passed onto the fluid itself will become less denser since it's hot, and it will start moving because of the convective action of the temperature convective action. So because of that, so it's indirectly related in some way. And then we have the chemical potential gradient. Now, chemical potential gradient is at the forefront of mass transfer. Why? Because chemical potential in itself is the reason why reactions can occur, or if any particle has any affinity towards the other, it might travel in that direction. And that is the exact reason why chemical potential gradient is also considered as a mass transfer driving force. So the answer for this question is the concentration gradient, pressure, and the chemical potential gradient, which can be considered as the direct driving force for mass transfer. Next, we have what is the mass transfer in the context of engineering and sciences? So we have again the four questions: the movement of energy between substances, movement of mass between phases, movement of pressure within a system, or movement of electrical charge between materials. Now, as we have seen, in simple terms, mass transfer means movement of mass between one place to the other. Now, that can occur between phases also and between systems also. So, that is the exact reason why it has been stated right here. Uh, when we talk about a system, it can be a thermodynamical system, closed, open system, and mass can transfer in that case also. And between phases, it can occur in between phases also. It can, the mass or the vapor forming from the liquid can go into the gaseous phase or the vapor phase. That again can occur. So between phases can also mean between two gases. They might be present at the same phase, but it is occurring between the same phase also. So we can define as that also. And then we have the movement of energy between substances. This cannot be considered exactly as mass transfer because only energy is being transferred. You can consider heat transfer in that case. So the movement of energy between substances can be accounted for in that way. The movement of pressure within a system is momentum transfer in a way. So we can understand by that analogy that movement of pressure within a system, like you can pressurize either one side or the other side. So pressure will create some kind of motion and that is related to the momentum transfer. And then we have the moment of electrical charge between the materials. That is straight away electrical conduction. So that won't be considered as mass transfer in itself. So among these four, the straightforward definition is movement of mass between the respective phases. Then next we have which factor does not affect the rate of diffusion. So it's saying does not affect. So we have to be careful about it. So first one we have is temperature. And just I explained in the first question, temperature does not directly affect it, but it will definitely it will increase the rate of diffusion. If we were to give sufficient energy to a particle or any kind of phase, it will get excited and it will give into the diffusion, which means that it will increase the rate of diffusion. So temperature definitely affects, and we are supposed to point out the factors which do not affect. Next, we have the surface area. Now, what happens with surface area is that one good example would be that if you have a chemical such as acetone, and if you pour it on the floor, the acetone is free to run in all directions, which means that it has unlimited surface area. And you can clearly see that as soon as you pour it, it starts evaporating the moment it hits the ground and it spreads in all directions because that increase in surface area helps in the diffusibility of the particular material. And then we have the concentration gradient. Definitely, concentration gradient is the direct answer for increasing the rate of diffusion. So if you have the higher gradient, it will definitely pass on more mass to the other side. So that is also affects the rate of diffusion. Then next we have the density of diffusing species. This is not related to the rate of diffusion. Why? Because it does not matter how dense one substance is than the other. For example, the less denser substance can also diffuse in the higher denser system. Vice versa also is possible. Why? Because you can use either of the above three mentioned factors to control the diffusivity of any kind of system. So if you have two systems, you can either increase the temperature of one of the materials and then that will start diffusing much better, or else you can play with the surface area or the concentration gradient in itself, which will be helpful in affecting the rate of diffusion. So density does not play a role in increasing or decreasing the rate of diffusion. So that's why density of diffusing species is not affecting the rate of diffusion. Next we have is in mass transfer, the Sherwood number is analogous to which dimensionless number in heat transfer. So we have been given four options, and I have given the explanation for all the four options right here. So we'll be able to point out much more clearly which one can explain the particular Sherwood number. So first we have is the uh, Sherwood number definition itself, which tells us it is the meaning of convective mass transfer divided by the mass diffusion rate. So it's saying that the amount of mass transferred because of the convection or the convective mass transfer term divided by the diffusion mass diffusion rate. Rate will occur with respect to the particular length over which it is diffusing. So that's why the term d by L is presented right there. And then we have the convective mass transfer coefficient, which tells us how much mass is being transferred or what is the affinity of the mass being transferred because of the convective coefficient. You can see right here, the convective mass transfer increases and the characteristic length also increases. That is the length over which the mass transfer is occurring. Your mass diffusivity, that is D, will be decreasing, resulting in increase in the Sherwood number itself. So that is the basic definition of the Sherwood number. Next, we will explore the options. Uh, let's take a look at the second option, that is the Reynolds number. That we exactly know what is Reynolds number. Reynolds number is nothing but the viscous force by the initial force. So it tells you that what is the which force is dominating, either the viscous force or the initial force of a fluid. So that is one thing. And the question is, we need to find out the number which is analogous to the heat transfer dimensionless number. So Reynolds number is related to fluid dynamics. It does have a role in the heat transfer dimensionless numbers also, but Reynolds number is directly not related to the heat transfer, and it's much more suited for the fluid dynamics model. Then we have the Nusselt number. Now the Nusselt number definition which has been given here is convective heat transfer divided by the conductive heat transfer. That is HL by K. So Nusselt number is very useful when we are talking about talking about a boundary place where the convection of the heat transfer and the conduction of heat transfer is occurring simultaneously. So which one is dominating can be found out using the Nusselt number. So we have the convective heat transfer, characteristic length, and the thermal conductivity. That is key. Next, we have the Prandtl number, which tells us the viscous diffusion rate by the thermal diffusion rate. Prandtl number is also used in the transport of heat from a surface using a fluid, and that is the exact reason why we have the viscous diffusion rate involved right here. And then we have the thermal diffusion rate also, which occurs because of the thermal conductivity of the fluid itself. Again, this phenomena also occurs at a boundary itself. And then we have the Peclet number. Now, Peclet number has a role in both, I would say, chemical reaction engineering and heat transfer also. And here we have the advective transport rate divided by the mass diffusion rate. Now, what is happening in the advective transport rate is what is the uh, transfer of mass happening because of the fluid flow velocity itself. So, because of the flow velocity, how much material is being transferred in either direction. And then we have the characteristic length over which the material is being transferred. And then we have the mass diffusivity term also. That is D. So, that term also helps in understanding what is the flow patterns being shown right here, and that's how the Peclet number is also defined. So among these, we can see the definition for Sherwood is convective mass transfer by mass diffusion rate. So among these all, the one which tells the like exact analogy for the heat transfer is the Nusselt number. As we can see, we have the convective terms on the top, then we have the conductive heat transfer or the mass diffusion rates at the bottom. So that is the exact way we can define for both the heat transfer and the mass transfer using the Sherwood-Nusselt number analogy. Next, we have the mass transfer is typically described by Fick's law. So what does Fick's law define? So it is basically asking what is the basic definition for Fick's law. So we have four options: the rate of heat transfer between materials, rate of momentum transfer between fluids.
It's like, please go,
Yeah.
please.
You have any doubts?
It's clear, clear, sir.
Yeah. Okay. So we have this. So mass transfer is typically described by Fick's law. And what is the meaning of Fick's law? It is asking. So we have the four options right here. And we have the rate of mass transfer due to convection, rate of momentum transfer between fluids, and rate of heat transfer between materials. So here is the definition. That is, movement of particles from high to low concentration is directly proportional to particles concentration gradient. That is defined by the Fick's first law of diffusion. So here are the notations which have been given. J is the diffusion flux, and that is proportional to d phi by dx, where d phi is the change in concentration or the concentration gradient, And dx is the change in position, that is the position your particles are traveling across the characteristic length, that is the x over which the entire mass transfer is occurring. Now we have a proportionality constant, that is d. That is nothing but the diffusion coefficient or the diffusivity. Now, what is this diffusivity? This diffusivity is the affinity of any particle to diffuse into the other. So the diffusivity is always described with the subscript A and B. Why? Because when one particle or one substance is diffusing into the other, we always want to define the entire system uh, with respect to either A or B. I'm taking, for example, A and B are two materials which are diffusing either A in B or B in A, or both are diffusing inside each other. That is the, like, what should I say now? Cases for the mass transfer diffusion. It can be equimolar diffusion, or it can be one phase stagnant and the other diffusing. So that can occur. So you can see right here, the red particles, when they are put inside the water, they're diffusing into the water. In the second picture, you can see they are growing apart. So that going apart is what is called the diffusivity, or basically the diffusion coefficient, which makes them spread inside the water, or the transfer of mass is occurring because of this. So the rate of diffusion of a component in a mixture. So that is the exact definition for the Fick's law. So now we have the last question. The effectiveness of mass transfer is improved by what? So what factors can help in improving the mass transfer? So first we have the reducing the surface area. Now that is basic knowledge that definitely surface area helps in increasing the mass transfer. So if you would reduce it, your effectivity will go down. Next, we have increasing the concentration gradient. Definitely, if you were to increase the concentration gradient, your effectivity of the mass being transferred will be much more efficient. So you can see that if you were to increase the mass transfer, increase the concentration gradient, the mass will transfer much faster across the characteristic length. And then we have lowering the temperature. Again, if you were to lower the temperature, you're basically reducing the potential energy of the particles itself, which are being transferred. So the affinity of mass transfer will be lowered. So that's why the effectiveness of the mass transfer will be decreased. Then fourth one is using thick barriers between phases. Now, definitely putting barriers between phases will hinder the mass transfer. So the correct answer for this question is the second one. So I hope I was clear in explaining these things. So if you have any doubts, you can ask me anything from previous classes or for this class also. Hello, hello.
Yes, sir, yes, I'm here.
Yeah, so you understood, right? If you have any doubts, you can ask me, like
Yes,
from
it's
previous
clear,
class
but
also.
one question.
Yeah.
Um, in which of the following states the matter does mass transfer occur? In which of the following state of
Huh.
matter does
Yeah.
mass transfer occur?
Okay.
So I find solids and liquids. Is it all the state? Because even this solid state, there is some possibility. Right? It can the water can diffuse in any sugar cubes. So
No,
is it all state?
see, if you are saying that water can diffuse, then there are two phases involved in that, because you have solid also and liquid
Yeah.
also.
Yes.
So what's being asked in the question is that
Uh,
both states should be same, and between them, if the mass transfer can occur.
okay. Okay.
Yeah. So solids won't be an answer because
Yes,
solids
yes.
cannot have that.
So
Yeah.
understand. I understand. So I interpreted that. So in that case, it is giving only liquids, only in gases. Gases possible, right? Liquids and gases.
Yeah, yeah, definitely,
So
definitely
two,
gases.
two answers I can give.
Hmm. Yeah.
Okay. Oh.
Yes.
But it takes only one answer. So is
Okay.
it liquid or solid?
Yeah, you can
Sorry.
give liquids, I guess.
That's right. So I chose liquid.
Hmm.
But I also have the tendency of giving gas also. So gas
Oh.
also the possible. So I don't know maybe which one is right. In which
Oh.
of the following states of matter does
Hmm.
mass transfer occur? Question
Okay.
number. So it is possible for you to see the assignment questions.
Uh, I cannot see it, but
Right?
I'll
I,
be
I
able to.
understand. I understand.
Yeah.
Because from the questions, I understand you are not getting it. From the previous classes, you are trying to match, isn't it?
Yeah.
Because some questions from week 4 also I could able to attend here. The
Okay.
previous, so it is a mixture. It's not the same thing what we are. I'm getting same
Okay.
sequence.
Okay.
Little here or there.
Hmm.
Maybe
So
it's a little confusion only. Let
no, no,
me.
no. It's fine. I understand. It's fine. I
Ah,
understand that.
yes.
So look, that's like if you have any other doubt, I can clear that also if you want.
Uh, now it is not much, but in the first and all, I had many. I think the coming classes, I can ask you all.
Yeah, sure, sure. Please
Explain.
attend. And if you have any doubts from the previous polymer courses, like previous
Yes,
polymer
yes,
lectures, you can ask me also.
yes. That time.
Yeah, sure. So yeah, I mean, I I only have these many questions to discuss because if I like,
Okay.
I think these are included in the coming assignments. So
Yes, yes, yes,
yeah, so
yes,
that's
yes.
why
It's great.
I'm not at
It's
liberty to discuss everything. So that's all.
it's okay. I understand. But whatever you are doing is sufficient. Uh,
Okay.
some confusions are there because you are giving answers for the other options also. That
Hmm.
gives us some clarity to understand
Yeah,
the questions much better.
exactly. Yeah, because I have to give the context for why all these options are also here. So like to
Mm,
explain the importance of the right answer.
yes, it's clear.
Yeah.
Thank you. I used to see you are again repeating the answers for recording. Is it? Are you doing again?
Uh, like you want me to repeat the answers?
Yeah. No. But I saw when the previous sessions, I
Hmm.
saw you repeating the thing. Maybe
Yeah,
late
I mean,
joiners.
no, I mean, like if somebody is trying to see this on YouTube, it will be like really clear for them. That's why
Okay.
I repeat
Oh,
the
okay.
answer once more.
Very nice. So as I said, if you are coming, mail, you can give me next month only. Are coming, right?
Yeah.
So if possible, shall we have a guest lecture?
I don't think
Or
I'll be
please,
able to give a lecture because I don't think I'm fit to give a lecture, first of all. So,
no, you can just tell them because our we are just to change our name from printing and packaging technology. From
okay, okay,
2019 only, we changed all the names and department. So we are new to the packaging field. So as you can say, just you can give some clarity about polymers and what are the recent research methods, not in the IIT level, okay, in the
okay.
application level, in
No,
the
I mean,
application.
like I don't want to give a lecture, but I can come there and interact with the students if that is
Yeah,
fine.
that's okay then. That is also fine.
Yeah, that I can do.
Mm, okay, that is
So
fine.
if they
You can
want
meet the
to,
students, give them some idea what to
yeah,
do, how to do.
exactly. Yes. So, you are like in like which department, which building it will be there?
Printing and packaging technology, which is adjacent to Knowledge Park,
Yeah, yeah, I know knowledge.
yeah, next to the Knowledge Park.
Okay.
opposite to information technology.
Okay,
Printing
fine.
and packaging is available only in CG,
Yes,
NIT.
yes. Yeah.
There is no other colleges.
Yeah, yeah.
Yes.
Okay, then
Yes, some
so
we are the faculty, Nirmala and Kanchana, both are doing this course just to
okay.
make us understand in depth so that we can guide some more students.
Yeah, sure.
Uh, PG are very less in number for us, only 12, 5, 6, 7. Likewise, only they'll be joining,
Okay.
maximum is
Yeah.
12. So
Hmm.
we want to give more attention to them and make them do some research on this topic.
Yeah, sure, definitely. Definitely I can.
Yes. Thank you, Rohan.
Yeah.
Thank you so much.
Yes.
Yes.
Hello. Yes, ma'am. Yes, ma'am. Yes, ma'am. I'll do that. Yes, ma'am. Yes, ma'am. Hmm. Yes, ma'am. Okay, ma'am. Yes, ma'am. Okay. Yes, ma'am. Publications. Yes, ma'am. List of publication is already there. Yes, ma'am. New things. Yes, ma'am. Yes, ma'am. I'll add that also. Yes, ma'am. I'll do that. Okay. No, ma'am. It's fine. It's fine, ma'am. Okay, ma'am. Okay. Yes. Sure. Okay. Yeah. Okay, then I'll start explaining now. So this is the fifth session for the polymer reaction engineering. Here we will be getting an introduction to the mass transfer involved in the polymer and the basics about the mass transfer involved. So first one we have is which of the following parameters can be considered as the driving force for mass transfer? Concentration gradient, pressure gradient, temperature gradient, and the chemical potential gradient. So we will explore the options one by one. So first one we have is the concentration gradient. And we can see that concentration gradient is the uh, main driving force for mass transfer, as in that if you want to see that always mass is transferring from the high concentration to the low concentration. One better example would be that the gases which are stored inside a cylinder. If you were to see that the inside the cylinder the concentration is higher than the outside. So if you were to open it, all the gas comes out, and because of that, the concentration gradient is achieved, and the mass is transferred from the higher to the lower until the equilibrium is achieved. Next, we have the pressure gradient. Now, the same example which I've just given you, pressure gradient also acts in a similar way, and it is also the driving force of mass transfer. Next, we have is the temperature gradient. Temperature gradient itself does not involve the transfer of mass, and it's not directly related to the driving. it cannot be directly said as the driving force for mass transfer, but it is indirectly related, as in that temperature gradient can help in increasing the mass transfer rates, which are already happening, as it provides sufficient potential or the kinetic energy to the particles so that the driving force can be increased. And next, we have the chemical potential gradient. So, in chemical potential gradient, what's happening is uh, the affinity of the particular material with respect to the other material which where the diffusion is occurring. So if it is chemically, if it is having the chemical affinity and if the chemical potential is higher, it will definitely diffuse into it. And that is exactly how thermodynamically you are defining the chemical potential gradient for the driving force of mass transfer. Next, we have what is the mass transfer in context of engineering and sciences? So this is a pretty basic question. And you can see from the options itself that movement of mass between phases is the uh, logical answer for this one, as it relates to the term mass transfer in itself. The moment of pressure within a system is related to more on the momentum transfer side of the system, and then movement of energy between substances can be conferred with the heat transfer itself. Which factor does not affect the rate of diffusion? So it is asking us which factor does not affect. So as I said in the first question itself, temperature is definitely directly affecting the rate of diffusion. If you were to increase the temperature, it will increase the potential energy and the kinetic energy of the particles, and it tells in the it helps in the diffusion process itself.
So screen was frozen. That's why I just raised.
Oh, s- oh, screen was frozen. Is it moving now?
Right now, after doing intervention, it started moving, but previous two slides are not. Just
Oh, okay,
repeat.
okay. So yeah, is it visible now? Is it moving now?
Yes, yes, yes.
Okay. So yeah. So the following parameters can be considered for driving force of mass transfer. As I explained, uh, concentration gradient, pressure gradient, and chemical potential are the answer for this. And mass transfer in context of engineering and sciences, we have movement of mass between the phases. That is the correct answer for this. And then which factor does not affect the rate of diffusion? So we have temperature, surface area, concentration gradient, and density of diffusing species. So as I said, temperature directly affects the rate of diffusion, as in it helps in increasing the potential energy and the kinetic energy of the particles with which they are transferring with which they are transferring the mass, and the process itself can be intensified because of temperature. Surface area also helps. What happens is that if you were to provide a larger surface area for the particles to spread out or to transfer, definitely they will take up the space and your mass transfer will be much more faster. For example, if you were to pour acetone in a beaker, or if you were to pour acetone in a flat plate, definitely acetone will evaporate faster from a flat plate than from a beaker. Then next we have the concentration gradient. Exactly as the name suggests, definitely if the concentration gradient is higher or lower, it will definitely affect the rate of diffusion. And then the fourth one we have is the density of diffusing species. So density of the species of the mass transfer species itself does not affect the rate of diffusion, as in if the particles are much more denser, they will travel slower or faster. That does not depend on it as much as the first three factors. So that's why density of diffusing species does not affect the rate of diffusion. So fourth one is the correct option. Next we have in mass transfer, the Sherwood number is analogous to which dimensionless number in heat transfer. So here we are asked to create an analogy between the dimensionless numbers of mass transfer and heat transfer. So in mass transfer, the Sherwood number is defined as right here. You can see convective mass transfer by the diffusion rate. So the mass transfer because of the convection and the mass diffusion rate which is occurring. So you can see right here, it is formed of three terms. Convective mass transfer, characteristic length over which the diffusion is occurring, and the mass diffusivity. So the diffusivity value that is D, and that gives you the Sherwood number. Now let's take a look at the four options and understand which one of them can be used for uh, explaining the Sherwood number analogy for the heat transfer. So we have the Nusselt number here. which is the convective heat transfer by the conductive heat transfer, that is HL by K. And you can see convective heat transfer characteristic length and the thermal conductivity are involved in Nusselt number, and it's a ratio of convective heat transfer to the conductive heat transfer. Next, we have the Prandtl number, where we have the viscous diffusion rate by the thermal diffusion rate, and that is applied at a particular boundary. So, viscous diffusion rate tells you how the viscous mass diffusion is occurring because of the fluid itself, and the thermal diffusion rate tells how the thermal conductivity is transferring the heat. So you can see from the expression itself, it says mu Cp, viscous diffusion, we have the mu term, that is viscosity, and we have thermal diffusion rate, we have the thermal conductivity term K. Next, we have the Becklet number, where it is given as the advective transport rate by the mass diffusion rate. So the mass which is being transported because of the advection process itself, and the mass diffusion which is happening on its own, is defined here. First is the flow velocity u, which is occurring because of the advective transport, and then we have the mass diffusion rate, that is diffusivity d by characteristic length. So among these, you can clearly see that the Nusselt number is the one which closely resembles the Sherwood number, where we have the convective mass transfer versus convective heat transfer, and mass diffusion rate versus conductive heat transfer. So you can clearly see that these terminologies are quite similar. And you can see if the length, characteristic length is increasing, the entire Sherwood number will be definitely higher. And same goes for the Nusselt number also. So Nusselt number is the correct answer for this question. Next we have is mass transfer is typically described by Fick's law. What does Fick's law define? So we have the four options right here. And I have given the definition for the Fick's first law of diffusion. We can see right here. Movement of particles diffusion flux from high to low concentration is directly proportional to particles concentration gradient. So you can see uh, J d phi by dx, or J is equal to minus d phi by dx. So you can see right here, J is the diffusion flux, d is the diffusivity or the diffusion coefficient, d phi is the change in concentration or the concentration gradient itself, and dx is the position. So you can say that the concentration gradient of the particles, which is forming right here, and from the example itself, you can see that when you're pouring the bunch of red particles into the blue water, how the red particles disperse around, and that process itself is described by the Fick's first law of diffusion. So the correct answer for this question is the fourth one, the rate of diffusion of a component in a mixture. Next we have is the effectiveness of mass transfer is improved by what? So it is now from the previous question, it is the opposite of that. It is asking how can we improve the mass transfer rates. So there are four options right here. First is reducing the surface area. Definitely, if you were to reduce the surface area, effectiveness of mass transfer will go down, as there is not sufficient area for the transfer of mass, and hindrance will be created in the small surface area. Then next we have the increasing the concentration gradient. Definitely, if you were to increase the concentration gradient, your mass transfer will be much more faster. Lowering the temperature again will indirectly affect the mass transfer, as in it will reduce the kinetic energy of the particles, and definitely they will be slower and the mass transfer will be hindered. And then we have the using thick barriers between phases, means the barriers which are involved. Using thick barriers between phases will definitely hinder the transfer of mass itself. So only these many questions are there for mass transfer. And if you have any doubts, you can ask me.
सर फर्स्ट वाला क्वेश्चन एक बार थोड़ा सा फिर से दिखाइएगा वो फर्स्ट
Huh. Which of the following parameters can be considered as the driving force for mass transfer? So here
ओके
there are four terms. Yeah, and amongst these, concentration, pressure, and chemical potential gradient are the direct driving forces for mass
ओके
transfer. क्लास 6 बजे ही शुरू हो जाती, तो फिर ज्वाइन करने में थोड़ा लेट हो गया तो क्या हो गया?
सॉरी सर, थोड़ा मैं उसके लिए बोलना चाहता हूँ। मैं सर आई एम वर्किंग पर्सन, सो दैट्स व्हाई मेरा थोड़ा आते-आते 6:30 हो जाता है। हर बार आप देखोगे मैं जॉइन करता हूँ बट आफ्टर 6:30 ही कर पाता हूँ।
No, no, it's fine. It's fine. No problems. No problem. Just asking the reason why. That's
Yes, sir. I am very regular, but during I'll get free from my office at 6:15,
Hmm.
like transport wise, and reaching up to my premises, it will take around me 6:30, 15 minutes. So
अच्छा,
during transport time, I just avoid to join.
अच्छा, अच्छा. Okay. Okay. Very good.
Sir, in last week,
Yeah.
likewise, there was a term about the quenching,
Quenching. Okay.
quenching of the polymer.
Hmm.
So likewise, it was having some equations like surface area. Like if
Hmm.
I state my product surface area, then it will affects also about the temperature.
Hmm.
So
Definitely.
right now, I just wanted to discuss about, sir. I just want to share that I work with high density polyethylene plant.
Okay.
So that's why my example or my queries are most related or relevant to that one only.
Oh, okay.
So,
Okay.
so actually, likewise, when we extrude a polymer,
Hmm.
so post extrusion, it will cool down like 220 degree to around 75 or 80 degrees Celsius.
Yes.
So likewise, some challenges we are facing, but someone is like telling us to reduce the temperature or below 50 or something like that. But as per our knowledge of the crystallinity,
Hmm.
we can't do that, just because if you do a sudden quenching in terms of HDP, the
Hmm.
crystal development is very poor and it will affect the further processing of the pellet as well as.
Yeah, definitely, definitely. Like you cannot do rapid quenching because that will directly affect your product quality also.
In LLDP, they are saying that we are doing that, but HDP where density is higher and
Hmm.
to and crystallinity is HDP is higher compared to LLDP,
Yes.
so we are not able to do that, or we can't do that just
Hmm.
to maintain.
Yeah. Like if you were to do rapid cooling, what will happen is you will lose your properties and it will be like, yeah, it won't be HDP as you know it.
Sir, it will be more helpful to me if you guide me some reference books or something like that, so I can go ahead with this direction about this topic.
Oh, okay. So can you just drop your email ID? I'll just tell you the names of the books there. I'll mail
Okay,
you.
sure,
Just
sure, sir.
just put it in the chat box.
Okay,
Okay.
sir. I'm
Yeah.
stopping it.
Okay, Prashant, I will definitely help you and I will let you know about the different documents or anything if I have any material on HDP. I will let you know. Sure.
Okay, thank you, sir.
Another thing, like what are the problems which you are facing? Like one thing is that it's like you cannot do quench cooling, but since you cannot do quench cooling, uh, are you having the issue in handling that polymer or something like that?
Mm, Likewise, sir, conveying. So conveying is
Okay, conveying is difficult, right?
difficult, but it's settled everywhere they can do, because I have worked with multiple organizations
Okay,
in big organization in India, big
yeah,
names. I'm not going to take the name, but last the three different organization in
hmm.
HDP,
Yeah,
they are using after pellet is developed, so there is no chances of further degradation due to oxidation or something like that.
okay,
So now normally pneumatic like air is directly used to convey the pellets,
hmm.
and big thing is that they and use gamma bands because this kind of specialty type of bands that prevents damage of the pellets due to rubbing each other or dust losses or something.
Okay. So gamma bands you're using. Okay, then sure. Then I will share with you some details about HDPE processing and what are the parameters involved in maintaining its crystallinity and the properties. Okay.
Okay, sir.
Yeah.
Okay, thank you, sir.
Okay, then yeah. Sure. If you don't have any other doubts, if you want, you can leave.
Okay, sir.